Okay, so yeah, so we got this computer, this accumulator machine, kind of working a little bit, but it's not super useful. Just mainly the problem we got here is that it only has one instruction, which is this add immediate to the accumulator instruction. So what I would like to do next is to try and implement a couple other instructions. Quickly, let me just go through how we can identify instructions. All right, so before we get started, let's talk about what the instruction format is here, just as a review. Here is my 8-bit instruction. And so we have, in the last part, we divided that up into kind of two pieces, right? We have an opcode, and then we have this immediate value, okay? Each of these is going to be 4 bits wide for now, okay? So, so the opcodes, we have 4 bits of opcode, so that means we have 16 possible combinations of opcodes, right? So we claimed 0, 0, 0, 0 for the opcode, add immediate to the accumulator. So that one is add immediate to the accumulator. And then, of course, the immediate value that's going to get added to the accumulator will be stored in this immediate field in the instruction encoding here. Okay, so the next opcode, so we have another 15 different opcodes, right? So let's just say, let's implement load immediate to the accumulator. Okay, so what this is going to do is it's just going to put a hard-coded immediate value into the accumulator register. Okay, and then of course we can have some other ones, we can define those later. We don't need to get into what those are going to be right now. But let's talk about this load immediate to the accumulator. So as soon as we have this second opcode here, now we immediately have a new problem, which is basically how can we distinguish between these two different kinds of the instructions, right? Type 1, which is this add immediate to the accumulator, and type 2, which is this load immediate to the accumulator. Okay, so these are two totally different kinds of operations that are going to put different things into the accumulator. So we need to be able to distinguish between the two. Okay, so what I want to do is I want to come up with a box, which is basically going to be an add immediate to the accumulator detector. Okay, it's going to be a 1 if if it detects that the current instruction is an add immediate to the accumulator instruction, and it's going to be a 0 otherwise, right? And then the input, of course, is going to be the 4-bit opcode of an instruction. Okay. So basically, the way the truth table for this thing is going to be laid out, we're going to have an opcode that goes into our detector, and we're going to have an output coming out from our detector. Okay, so here's my long truth table here with all the possible opcodes that we could have in this computer. And of course, the output is just going to be a 1, right? This is the only instruction that's an add immediate to the accumulator here, is this first instruction, right? This opcode codes for add immediate to the accumulator, right? So for all the other opcodes, the output of this box is going to be a 0. Okay, so how are we supposed to build this thing, right? Seems kind of challenging. So if you look at this truth table, it's kind of like the opposite of a 4-input AND gate. So if the 4-input AND gate, let me just draw a 4-input AND gate here. All right, so 4-input AND gate basically has 4 inputs, okay, A0, A1, A2, and A3. And its output is going to be a 1 if all of the inputs are 1 and a 0 otherwise. So that's not exactly what we have here, right? What we have here is we have a truth table or some kind of a logic device that generates an output of a 1 if all 4 inputs are 0, right? So it's not, I don't know, it's a little bit different, right? So how can we change this thing around a little bit to make this work, right? So one thing we could do is we could run all of our opcode inputs through an inverter, okay? So let's say I have my opcode. I'll call it O0, O1, O2, and O3 to represent the 4 bits of the opcode. All right, each one of these is one of the bits in the opcode. So what I'm going to do is I'm going to run each bit through an inverter, and then I'm going to take the output of that inverter and run it through a 4-input AND gate. Okay, so let's see what that gets us. Let's try this for a second. I'm going to erase some of this stuff here. I'm going to write this as opcode bar, which is just the bitwise knot of all the bits in the opcode. So opcode bar just has it's basically the bitwise inverse of opcode. So if we have a bit, for example, I'll show you here. If we have a bit in the opcode here, the first row, right? That's a 0. It gets in opcode bar, it gets converted to a 1, right? If it's a 0, it turns into a 1. 0 turns into a 1, and so on, right? Okay, and then if we have a 1 in our original opcode, I will color code that with a different color here. If I have a 1 in my original opcode, that bit turns into a 0 in opcode bar. Okay, so we ran all of the bits through an inverter, and now if we take all these bits, if you look at the first opcode here, whoops, didn't mean to do that. If you look at the first, if you look at the bits of the opcode, you'll see that all 4 of them are 1s. Okay, so if all 4 of those bits are 1s, we can pass that through an AND gate, right? And so if we AND all 4 of those bits together, we can say opcode 0 and opcode 1 and opcode 2 and opcode 3. If we AND all 4 of those bits together, we're going to get a 1. Okay, but if you look at all of the other combinations, all the other combinations of this opcode contain at least 1 0. Okay, so like for example, in the second row has a 0 in the least significant position, right? Because there was a 1 in the least significant position of the positive opcode. Okay, so if I AND the second row together, I'm going to get a 0. And the same is true for all of the other possible combinations of opcode bar. Okay, so what I can do to build my detector here, this is my detector for the opcode instruction. This opcode detector detects of an add immediate. Okay, so this is going to be a 1 if the opcode is 0 0 0 0. Okay, so we need to build this thing, okay, to detect if we have an add immediate to the accumulator. So we'll do that in a second. There's one other opcode I want to look at here for a second, right? So the second opcode that I want to build is, if I go up here to my proposed opcode table, right? So the second opcode that I want to build here is this one for load immediate into the accumulator, and that opcode is 0 0 0 1. Okay, so if we go down here, let me just erase some of this stuff real quick here. Okay, so what we want to do here is we want to find a detector for detecting the load immediate to the accumulator now, right? That's going to be the second row. All right, so now all the bits are not all the same, right? We have 3 zeros and a 1 in the opcode, 0 0 0 1. Okay, so what we need to do is we need to find some kind of a gate combination that we can use to basically produce a 1 when we see the combination 0 0 0 1. Okay, so we can use an AND gate again. So we're going to AND all 4 of these signals together, but we're not going to AND all 4 of the inverses together this time. Okay, we're going to AND, looks like what we have here is the first 3 inverse bits are 1 when we have this opcode, and then the last positive bit, right, the last regular bit, uninverted bit, is a 1. Okay, so what I want to do here is I want to say opcode 3 inverse, that's this guy, ANDed with opcode 2 inverse, that's the second one here, ANDed with opcode 1 inverse, ANDed with opcode 0, no inverse. Okay, so if we do that, if we apply this to the second row, opcode 3 inverse is a 1. Okay, ANDed with opcode 2 inverse is a 1. ANDed with, oh, that's a terrible AND sign there. ANDed with opcode 1 inverse, also a 1. ANDed with opcode 0, that's the 0th bit of our regular opcode. That is also a 1. Okay, so what we're going to do is to detect this opcode, 0001, we're going to invert the most significant 3 opcode bits. We're not going to invert the least significant opcode bit. We're going to leave that one alone, and then we're going to AND all that stuff together. So let me show you how that works. Okay, so we have opcode 0, opcode 1, opcode 2, and opcode 3. Okay, we're gonna invert these 3 bits here. We're not going to invert opcode 0, and we're going to pass all of this stuff into a 4-input AND gate. And the output of this 4-input AND gate is going to be 1 if the opcode is equal to 0001, right? So this is a load immediate detector, load immediate to the accumulator detector. Okay, let's build this thing in hardware. Okay, so let's get started actually trying to implement this load immediate instruction. So basically what we want to do with this load immediate instruction is we want to take the immediate field from our opcode that's coming out of the instruction memory here, and we want to directly put it into our accumulator. Okay, so you can see our accumulator over here. Basically, the thing about the accumulator at this point is that the only input to the accumulator can come from at least the way that we have it structured right now. The only input from the accumulator can come from the adder. Okay, right now the only instruction that this machine implements is add immediate to the accumulator, right? And if you recall from last video, the way that works is we take the immediate field, which is coded into the instruction. It's the least significant 4 bits, or the least significant nibble of our instruction. We take that immediate field, the bits 3 down to 0 of our instruction. You can see those go right here. We shove that into the adder on one of the inputs of the adder, and the other input to the adder is the current value of the accumulator, right? So we take the current value of the accumulator, we add it to the immediate field from the instruction, and then out pops the sum of those two things, and that's what comes into this D-in port of our accumulator, right? So what we need to do is we need to implement a new path to get data into this accumulator. And the way we're going to do that is we're going to use a multiplexer, right? We're going to use this 2-to-1 multiplexer that we talked about a little bit earlier. And what this thing is going to do is it's basically, oh, that's not good. This thing's going to basically allow us to have 2 different ways of getting data into our accumulator, right? The first way, the first way that we can get data into our accumulator is through the adder, and the second way we can get data into the accumulator is going to be through the directly, just by feeding it directly from the instruction. Okay. So there's 2 possible inputs to this accumulator. Let me just try and move this. I'm going to move this thing down a little bit here so that we can line it up a little bit better with the multiplexer. Just give me 1 second to do that. Okay, so now we have this multiplexer here, and the multiplexer is going to allow us to select if we have a 0 coming in the select port, then that's going to allow us to select the data coming from our adder. And if we have a 1 coming from our select port, then that's going to tell the multiplexer to select the data that comes directly from this immediate field. We need to make sure the bit width of this thing is the same as the bit width of the data that it's processing, so 4 bits. And then this select signal, this is the control signal here that's going to tell the multiplexer which path should be taken. Should we either come from the adder or come from the multiplexer, right? If we're doing a load immediate instruction, we want to come from the instruction, right? The immediate field of the instruction. If we're doing an add instruction, we want this multiplexer to give us the data from the adder. Okay, so we need to figure out how to set this this select signal correctly. Okay, and that's going to be done by this instruction detector. Okay, so if the instruction detector detects that we have a load immediate field, then we're going to, or the load immediate instruction, we're going to set the select field to a 1. Okay, otherwise we're going to set it to a 0. All right, so let's build those instruction detectors. So we're going to build those inside of a subcircuit. Whoops, I'm going to create a new subcircuit. And this is going to be called the control logic. Or the decode, I'll call it the decode logic. All right, that's usually what it's called in computers. Okay, so the decode logic, we're going to build inside the decode logic a couple of these detectors like we had discussed the last time. Okay, so what you can see I'm doing here is I'm taking my input, which is going to be my the bits that are coming from my instruction. Okay, oops, that's not right. And I'm going to take that input and I'm going to split those bits up. These bits are going to come in from my instruction. This is my instruction opcode. Okay, and there I'm going to split those bits up into 4 individual bits. They come in on one 4-bit bus. I'm going to split them up into 4 individual bits. And then I'm going to build, you can kind of see me building the add immediate opcode detector here, right? We're going to invert every bit, and then this signal here is going to be, let me see if I can, I guess I can't name a signal, right? So this is going to be an add immediate to the accumulator. Okay, so this is going to be true if the instruction is an add immediate to the accumulator. Okay, let me just copy paste this down here, and this is basically, we're just going to replicate this. This is going to be a similar type of a thing. This is going to be in a detector which is going to detect and load immediate. Okay, then what I'm going to do is I'm going to take my opcode signals from up top here, and I'm going to bring them down below to the second instruction detector. I'm going to try and keep things as organized as possible. Okay, so this is going to be load immediate to the accumulator. All right, cool. Okay, and then one of the outputs of this thing, there's going to be many outputs from this control logic block, but one of the outputs from this control logic block is going to be the multiplexer signal, which is going to select the input for the accumulator here. Okay, so if we have a load immediate, we want that input to be coming from path 1 on this mux, right? So we want to come from our instruction through this mux into the accumulator. Okay, so they want a 1 if we detect a load immediate. Okay, load immediate to the accumulator, right? Otherwise, we want a 0. All right, so let me make an output here. This output is going to be called accumulator DN mux select. Right, this is the select signal for the accumulator DN mux. Right, the accumulator DN mux is this mux right here, and that's going to be, like we discussed, it's going to be a 1 if we have a load immediate instruction. Okay, so here's the decode logic. That name was a little too long. Let me change that name. It's a little too long here. Accumulator, I'll make it ACC DN mux select. All right, let's try that. That's a little shorter. Here we go. It's still a little too long, but we're going to go with it. Okay, so, all right, so here's my decode logic. The input to my decode logic is going to be the opcode of the instruction, right? That's this opcode right here. And the output of the decode logic is going to be the select signal for this mux, right? Okay, so now we have two different kinds of instructions, right? We have the first kind of instruction is going to be an add immediate. That's coded by 0 in the first nibble of the instruction. So you can see all of the instructions in my instruction memory right now. These are all add immediate instructions. Okay, if I want to do a load immediate to the accumulator instruction, I'm going to put a 1 in the first nibble. Okay, so let me make this 1F. Okay, so the first instruction now is going to be 1F. And what that's going to do is it's going to be instruction opcode type 1. That's a load immediate into the into the accumulator. And the immediate value that's going to get loaded is F, right? 4 1s. Okay, so let's, whoops, I better hook some of this stuff up here though. It looks like some of this is disconnected, so it's not going to work unless we connect this wire here. Okay, all right, so 1F is going to load the value F. Okay, and then 0.3 is going to add the number 3 to the accumulator. 0.2 is going to add 2 to the accumulator, and so on. So let's reset the processor here. Okay, so you can see my first opcode is 1F. All right, and then if I hit this clock button, you can see that we have inserted the number F into this accumulator value, right? And the next instruction is going to add 3 to that, so it's going to be F plus 3 is F 0 1 2, so the output here should be 2 on the next clock. Let's do that. There's the 2, then we add 2 to that, that's going to be 4, and so on. Okay, and then the rest of the instructions are all zeros. They're not going to do anything. All right, so let's reset this thing one more time, and just let's see what's going on. That reset. Oh, here we go. The reset. All right. So, okay, so 1F, right? So 1F, you can see the opcode that's being read out of memory is 1F, right? The 1 here is going to be the actual, is going to be the opcode of the instruction, right? And you can see that the decode logic is taking that opcode, the input to the decode logic is the opcode of this instruction. It's taking that 1, 0 0 0 1 on the input, and it's generating, it has this load immediate to the accumulator bus signal here has been activated. So it has correctly detected that we're trying to load an immediate to the accumulator, right? And the output here, right, this accumulator DN mux select now is now being generated as a 1, which is causing this multiplexer to select the F. This is an F here, which is coming from our instruction, right? So the instruction immediate value is an F. It's getting routed through this multiplexer to the input of our accumulator. And then when we hit the clock, whoops, when we hit the clock here, if I can zoom correctly, then you will see that that F is getting loaded into our register, our accumulator register. Cool. Okay. So that is the load immediate to the accumulator instruction.